Happy to have this our speaker today, Dylan Airey. He'll be discussing generic points.
Okay, yeah, so thanks for having me and thanks for coming to my talk. So just to start off, to sort of motivate some of the questions we asked, I want to recall the pointwise ergodic theorem. What this says is that if x is equal to a Polish space, it is a separable, completely metrizable space, and x, t, mu is an ergodic dynamical system. Then, for mu, almost every x, and for all bounded continuous functions on x, we have the following. So if we take the time average of our continuous function f over the orbit of the point x, this is in fact equal to the spatial average of f. Right. So this is, sort of a specialized version of Birkhoff's pointwise ergodic theorem. Right.
So isn't it just exactly Birkhoff's theorem?
I mean, because you can say for like L1 functions, I don't think you need like it being a Polish space.
You assume that f is continuous, right?
Yeah. Here, I'm just going to get this. Yeah. All right. So yeah, so this is the pointwise ergodic theorem, right? And so in particular, you might ask a question about, okay, well, what is the set of points x where this theorem holds? What does that look like? So we know it's a full measure set when mu is ergodic by this theorem. So just as an example, if x is 0 to 1, not including 1, mu is equal to the Lebesgue measure. And t of x is equal to bx mod 1, where b is some integer greater than or equal to 2. Then the points. Okay, so this is an ergodic dynamical system. So the points satisfying the ergodic theorem. Right, these have a name. These are the normal numbers in base B. These were actually defined, much earlier, or well, not much earlier, but just before the ergodic theorem in 1909 in the context of large numbers. All right. So this is just sort of an example of a set of points which satisfies this theorem. So here are some facts. So this set, which I'm just going to call the generic points for our dynamical system. If mu is ergodic, these are always full measure. So if we look just at normal numbers, yeah, these are full measure. They have full Hausdorff dimension. Oh, sorry, the complement has full Hausdorff dimension. So the complement has Hausdorff dimension 1. And the set of normal numbers in base B is meager. Right, so these are all sort of different notions of...
These are statements about this.
Normal numbers, sorry. Normal numbers.
Okay, I was going to say,
yeah. Normal numbers in base B. So these are all sort of notions of size of this set, right? So it's full measure, so it's large in the measure theoretic sense. Its complement has Hausdorff dimension 1, so its complement is large in the sense of Hausdorff dimension. It's meager, so its complement is large in the sense of co-meagerness. So now we can ask the question, okay, well, what about other expansions? There are other interesting expansions besides just this B-Airey expansion, which is sort of naturally associated to this shift map here. So for example, you might be interested in the continued fraction expansion, where now x is equal to 0, 1, minus the rationals, and t of x is equal to 1 over x mod 1. And then we have a Gauss measure, which is absolutely continuous with respect to the Lebesgue measure. Or you might be interested in, so this is the continued fraction expansion. Or you might be interested in beta expansions. So here, x is again equal to 0, 1. But t of x now, it's equal to beta x mod 1, where beta is some non-integer real number. So this is now a discontinuous transformation of the unit interval, right? Or a discontinuous transformation of the circle. So there's all sorts of these interesting number theoretic expansions that are naturally tied to a dynamical system, and we can ask the same question. The normal numbers for these continued fraction expansions, do these have the same property, or the same thing for beta expansions?
Yeah, by the way, that your beta is just not integer. What do you know
Irrational.
about the...
Or you want beta to be like a rational, really?
Yeah, irrational. What do you know about the existence of invariant measure?
Yeah, so this is called the Perry measure, or sort of one of them is called the Perry measure. I don't remember the formula for this. It's kind of complicated, but it is an invariant measure for this guy, and it's absolutely continuous with respect to the Lebesgue measure. So yeah, there's a nice sort of invariant measure associated with this dynamical system. And here we have the Gauss measure. All right.
Yeah, excuse me, I am just thinking. So, from what you said, how does it follow that this transformation is ergodic?
I mean, you can work out sort of the details, but yeah, this is ergodic with respect to this guy. And this is ergodic with respect to that.
Yeah, so why it is ergodic with respect to this measure? Do you know?
I mean, I guess the Perry measure is sort of this measure of maximal entropy on the beta shift, right?
No, I don't think so. The
Okay.
measure of maximal entropy is probably singular.
Hmm. I'm not sure. But it is a fact, though.
It is true, but yes, maybe short proof.
Yeah, I'm not sure, sorry. All right. So, if we sort of write out the condition for x to be, a normal number of base b, for example.
Excuse me if I interrupt you.
No, please interrupt as much as possible.
You are here for the first time, but we always interrupt the speaker. Yeah. So if you replace beta by some function of x, so under what condition this transformation will have an invariant measure?
Where you take f of x times x mod 1, or just f of x mod 1?
Just beta x times modulo 1, but beta is not a constant, but something else.
I'm not sure. I've never really thought of that. I mean, I think maybe our theorem can tell you that if you have at least two invariant measures and beta satisfies some properties, then you'll have the same result about what I'm going to talk about. But I'm not sure.
Okay, very good.
Yeah. So, I mean, for example, there are sort of generalized Roth series expansions, which are given by just take some partition of the unit interval into subintervals, and then take the transformation, which maps each unit interval linearly onto 0, 1, like this, or possibly reversing orientation too. And this is a generalized Roth series expansion, so this is like a subclass of those things, right? Just depending on which interval x lies in. And so what I'm going to say actually does apply to transformations of this type. And these always have invariant measures. It's just a leg. But I'm not sure about more general possible beta of x's. Okay, so if we actually write out what it means for a number to be normal in base b, what this says is that x is normal. And instead of writing this out all the time, I'm just going to say it's in the set N of b, so this is the set of normal numbers in base b. If the following holds, so for all blocks b in 0, b minus 1, so all finite blocks of digits 0 through b minus 1, there exists an n, natural number n, such that for all n greater than n, we have the following. So if we look at the absolute value of 1 over n times the cardinality 1 less than or equal to I less than or equal to n, such that. So if we look at the base b expansion of x, x can be written uniquely if we don't allow trailing b minus 1s as the sum from I equals 1 to infinity of bi over b to di. Right, and then multiplying by b mod 1 is just the same as shifting over the sequence of digits, right? So if we look at, in the base b expansion of x, if we look at positions I to I plus k minus 1, which I'll denote by this, so x of I to I plus k minus 1, the frequency with which the block b appears in the base b expansion of x minus 1 over b to the length of b, that this tends to 0, right? Or so really I should say for all epsilon greater than 0, so for all epsilon greater than 0, there exists a natural number n such that for all n greater than n, the frequency with which b occurs in the first 1 to n digits of x minus 1 over b to the length of b, that is the measure of the cylinder set associated to this block b, that this is less than epsilon, right? So we see that this set here, not including all these conditionals, this set here is open set, right? Open in the, if we take the product topology on 0 to b minus 1 to the n, right? And so what we see is that, we're taking a sequence of open sets, we're taking a countable intersection, a countable union, and then epsilon we can just take to be, some rational greater than 0, another countable intersection, and then another countable intersection. So we can write the set n of b as equal to a countable intersection of a countable union of a countable intersection of open sets. And so now the question is, can you do any better than this? Can you find a simpler representation?
The question, is it possible to consider in this expression epsilon depending on n, so that epsilon depending on n tends to 0 as n tends to...
So I mean, this will be like finer information than just what you care about for like the ergodic theorem. So I guess this would be like a central limit theorem type thing, like a sort of rate of convergence of this guy. So we don't consider this, but I mean, you could, I suppose. But the point I want to make is just that as we've written it, we can write this as a countable intersection of a countable union of a countable intersection of open sets. So that's sort of the point of the way I've written it here. Right. So the question is now, can you do any better? You know, can you instead maybe write it as just a countable union of a countable intersection of open sets? And so to formalize this question, I need to introduce the Borel hierarchy. Right. So the Borel hierarchy is sort of a partition of the Borel sigma algebra of your Polish space X. You know, any Borel set can be written as sort of a countable union of a countable intersection of a countable union. You know, possibly doing this some countable ordinal of times of open or closed sets. Right. This is the definition of the Borel sigma algebra. So we can stratify this into a couple of different classes. So first, we consider the class sigma 0, 1. We'll let this be the open sets. And we'll define pi 0, 1 to be the closed sets. Next, we'll define sigma 0, 2 to be countable unions of elements in pi 0, 1. So in other words, countable unions of closed sets, these are F sigma sets. And similarly, pi 0, 2, this is going to be countable intersections of sigma 0, 1 sets. So countable intersections of open sets, that's G delta. Right?
Yeah, but sometimes it can happen that the set which you obtain in this way have measure 0, right?
Mm-hmm. This is not talking about measures at all. We haven't fixed a measure at all on X yet. I'm just talking about the Borel sigma algebra on our Polish space.
Yeah, but if it were so, then Birkhoff Ergodic theorem is not applied, right?
Yeah. So yeah, certainly there can exist, you know, measure 0 sets. Well, not open sets, obviously, but I mean, I'm not. This is sort of a separate discussion. This is just talking about classifying the complexity of this set here, which is sort of a separate question than, you know, the size of the set in measure theoretic terms, right? Just like, you know, measure theoretic largeness versus topological largeness are different questions. This is a different question than sort of measure theoretic largeness. Anyway, so this is our F sigma sets, and these are G delta sets, and we can sort of iterate this construction and construct sigma 0, 3 and pi 0, 3. Pi 0, 3 being countable intersections of sigma 0, 2 sets, and sigma 0, 3 being countable unions of pi 0, 2 sets. And we can also construct one more point class, and these are the delta 0 ends. So delta 0, 1 is just the intersection of pi 0, 1 and sigma 0, 1. So it's the clopen sets. So if, you know, X is connected, just empty set in the entire set X. Delta 0, 2, sets which are both F sigma and G delta. And pi, delta 0, 3, so on. And so we get the sequence of containments. So delta 0, 1 is contained in both of these guys. Both of these guys are contained in delta 0, 2. Delta 0, 2 contained in these classes, and so on. So we get a hierarchy of these sets, worked by containment. So in general, we need to define this for countable ordinals. So for a countable ordinal alpha, sigma 0 alpha. So we say that a Borel set A is in sigma 0 alpha if there exists sets AN in pi 0 beta n, where beta n are ordinals less than alpha, such that A is equal to the union of all ANs. And then A is in pi 0 alpha if X, if the complement of A is in sigma 0 alpha. Okay, so this is how we define this in general. And so the point is that, because of the definition of our Borel sigma algebra, any Borel set is going to lie in some sigma 0 alpha or pi 0 alpha. Right, so we exhaust all our sets. And in fact, if X is an uncountable Polish space, then all of these classes are distinct. For every alpha, there exists a set which is pi 0 alpha, but not in delta 0 alpha. Okay. So this is sort of a notion of largeness. Okay, so now we say that A is sigma 0 alpha hard if the complement of A is not in pi 0 alpha. And then A is sigma 0 alpha complete if A is sigma 0 alpha and sigma 0 alpha hard. So what this is saying is that if you're sigma 0 3 complete, then you're a sigma 0 3 set, but you can't be anything lower. Anything lower complexity is not sigma 0 3 hard. Okay, so by this argument here, we know that the set of normal numbers in base 3 is a pi 0 3 set. Open sets are sigma 0 1, so we have a countable intersection, countable intersection of the countable union of the countable intersection of sigma 0 1 sets. That's pi 0 3. So another question is
3 intersections, right?
Yeah, countable intersections and countable unions.
The letter 3 is connected with how many there?
Exactly. Yeah. Okay. So Kempers asked this question then in the 90s: is the set of normal numbers in base 3 pi 0 3 complete? Is it any simpler than pi 0 3? And this was answered in the affirmative by Key and Linton. And a B is pi 0 3 complete. Now I'd like to give a proof sketch, but I don't really have time for it. So what I will say though is sort of a general strategy for showing that something is pi 0 pi 0 alpha complete. It's very similar to showing that a program is uncomputable. Right. So the idea is that you know that the halting problem can't be solved. So you reduce the question of whether of solving your problem to the halting problem. The halting problem can't be solved, so you certainly can't solve your original problem you started with, right? So it's a very similar strategy. This is called the reduction method. So the idea is that if A in X is sigma 0 alpha hard, B is a subset of another Polish space Y, and F from X to Y is continuous, such that F inverse of B is equal to A, then this implies that B is also sigma 0 alpha hard. And this isn't too hard to see, right? So because we're taking a continuous inverse, countable intersections and countable unions, we can just bring outside the inverse, right? And so a continuous inverse of an open set is open and a closed set is closed. So in particular, if A could be written as something lower than, or if B can be written as something lower than sigma 0 alpha, then A can as well, which contradicts A being sigma 0 alpha hard. And is this clear? Okay, so this is the reduction method.
So what's the halting problem kind of example in this case? Like, what did they pass to show?
So, I will show these sets, but for example, for pi 0 3, which is what I'm going to be interested in, the set is all sequences of natural numbers such that the limit is infinity. This is pi 0, 3 complete. Right, because this is equivalent to, say you have an infinite two-dimensional array. This is equivalent to, in each row, only having a finite number of ones. And so you can check that this is naturally a pi 0, 3 set, and it turns out you can show, I'm not sure how, but you can show that it's pi 0, 3 complete. And you can sort of generalize this construction for higher n. Okay. All right. So the question is now, for this B shift, we have that the generic points are pi 0, 3 complete. And we want to know the answer for other dynamical systems. So here's the main question. For which dynamical systems is the set of generic points pi 0, 3 complete? All right, so some basic assumptions we have to make on our dynamical system. We need to assume that T is continuous, really, for any hope of this to be true. So need T to be continuous, right? And the reason this is so is because we're working with sort of the lower tiers of the Borel hierarchy, right? Any uncountable polar space is going to be Borel isomorphic to 2 to the z. So in particular, the set of generic points, set of normal numbers in base B is an uncountable polar space, and so it's Borel isomorphic to 2 to the z. And so we can find some map phi from M of B to 2 to the z, right? Which is a Borel isomorphism. Let's say 2 to the n. Okay, so then if we look at the system 2 to the z, T prime, where T prime is the shift on n of b, but sort of on this space now using this Borel isomorphism phi here, right? And then we look at the push forward measure of the standard IID uniform over 0 through b minus 1 measure. If you look at this guy, then every point is generic, right? Now, T prime is certainly not continuous on this space, since we don't have any, this map is not going to be continuous. But the point is that, this generic points is everything, so this is going to be a delta 0, 1 set, right? So it's certainly not pi 0, 3 complete. Okay, so we are going to need some type of continuity for T. But that's not enough. So just to list some examples of systems where we don't have pi 0, 3 completeness. So example 1, just the irrational circle rotation. Right, here every point is generic, right? N alpha is always uniformly distributed mod 1, and so x plus n alpha is always uniformly distributed with respect to the Lebesgue measure. And so, every point is generic. So this is again delta 0, 1.
So it is. So the statement is true for any just group automorphism of an abelian group.
Yeah, because they're all uniquely ergodic, right? Yeah. So unique ergodicity breaks this theorem, and that actually is going to be an assumption that in order to get pi 0, 3 completeness, we're going to assume that there are at least 2 invariant measures. So yeah, another example.
technical entry about the previous question. So if we consider the multiplication by beta, how many ergodic invariant measures does it have?
There's at least two, just because the point at 0 is...
But at least two, but it's but
that's all we need for the theorem, is that there's at least two. So I'm not sure how many there are. I guess, I mean, certainly infinitely many. I guess it's like infinite dimensional. But all we need to get for our theorem is that there's at least two.
Yes, I want to say that the set is uncountably many.
Mm-hmm.
So there are very many ergodic tests.
Okay. Thanks. All right. So now, if we let t of x be x squared, where our polar space is the closed unit interval, right? There are two ergodic invariant measures, point mass at 0 and point mass at 1. Right, and so what you have is that the set of generic points of mu, so I'm just going to write this for the generic points of mu, this is equal to the interval closed at 0, open at 1, whereas g of nu is equal to just the singleton 1. Right? So here we have a sigma 0, 1 set, here we have pi 0, 1 set. So far we've filled out these three parts of the Borel hierarchy. And we want to get also these, presumably. Now I do want to say that if you assume that T is mixing, then you can't have an open set of generic points. It does need, or it can't be open.
Mixing with respect to which matter?
Topologically mixing. Yeah, so I mean, in this case, not topologically mixing, so yeah, it doesn't. That's why we can get this this sigma 0, 1 set here. All right. So when we were first sort of thinking about this problem, I thought, okay, well, if you sort of look at the original key Linton proof for normal numbers, the idea is to take your infinite sequence here and do some clever thing where you start with a generic point and you sort of change along certain blocks the value of this generic point according to beta. And you need sort of enough ways to change it to make this proof work. And so I thought, okay, maybe some positive entropy type condition could be necessary here. And that's not true. It's not sufficient. And this is just by the Jewett-Krieger theorem. Right. Any Dynamical system has sort of a uniquely ergodic representative, and so in particular we have uniquely ergodic systems with positive topological entropy and measured theoretic entropy. But unique ergodicity, every point is generic. So this shows that having positive entropy isn't enough. And to actually see that every point is generic, an alternative definition of being a generic point, and the one that we're going to use, is that if you define E of xn, let this be sort of the nth average over the orbit of x. So 0 minus 1 point mass at t to the ix. Right. Then x is generic if the limit as n goes to infinity of these empirical measures is equal to mu, where this isn't the weak star limit. Right? That's really just the statement of the ergodic theorem. Right? Okay. Last example I want to give. So there's a construction by Falniowski, Kulczycki, and Lee. So they constructed a closed subshift. Such that every point is periodic. Or the limit as n goes to infinity of 1 over n times the number of recurrences of the digit 0, such that this line is equal to 1. So either every point is periodic, or it's just going to be asymptotically all zeros. Right? Okay. So then, I do want to keep this up. Right. So if you look at the generic points of the measure, just supported with a single point of all zeros, then this is going to be the complement of the set of periodic points, and there are only going to be countably many periodic orbits in this closed subshift. And so this is pi 0 to complete. See, we don't quite have a construction yet for sigma 02 and delta 02, but we can get pretty much anything below pi 03. Okay. Now, it turns out that a nice property that's very sort of important in other areas of dynamics that does imply that the set of generic points is pi 03 complete. And this is the specification property. So this was actually first introduced by Rufus Bowen in the context of axiom A diffeomorphisms. So a lot of very interesting dynamical systems do have specification, like geodesic flows on negatively curved manifolds. That's any sort of like hyperbolic system, any axiom A diffeomorphism. So specification property. In the time since Bowen introduced this definition, there have been a lot of different notions of specification that have been introduced. I think we looked through the literature, and there were at least 14, all with very interesting names like almost specification, almost star specification, weak almost star specification. It goes on and on. It's gross. So we had a lot to choose from, and we settled on the following, just because it's a specification property that in particular is satisfied by the beta shift. That was really sort of the key thing we wanted to get an answer for, if anything. So this definition is right almost star specification. And this is defined for symbolic shifts. I'll define a notion, or I'll mention a notion of specification for more general dynamical systems, but the first theorem I'm going to state is just for symbolic shifts. So,
it's symbolic to shift, right?
And countable alphabet.
Huh?
Countable alphabet, yeah. Any countable alphabet. Almost star specification. So we say that subshift has this right almost star specification property. If there exists a set G in the language of X, that is the set of words where the cylinder set for that word intersected with X is not empty, right? So all allowed words in X. Such that for every epsilon greater than 0, there is an n equal to n epsilon such that if U and V are in our language, and they have length at least n of epsilon, and U is in G, then there exists a V prime in G such that the following conditions hold. So first, the length of V is equal to the length of V prime. Second, the Hamming distance, the normalized Hamming distance between V and V prime, that is, the total number of places where V and V prime differ divided by the length of the word. This is less than epsilon. And U, V prime is in G. Okay. So what does this actually mean? Well, it says that if you want to concatenate two words together, and the first word is in G, then you can almost do this. You just have to slightly change the second word. And this is sort of in the spirit of these general specification properties. Bowen's original definition of specification was if you have orbit segments in your system, then you can find an actual orbit that very nearly traces out these orbit segments. Right? So you can always paste together partial orbit segments into a full orbit segment as long as you sort of wait enough in between these orbit segments. And this gap is going to be constant. So this is sort of in particular, right almost start specification is implied by the specification property. So that is true. All right. So here's the theorem. Our first theorem that we proved. So let A be countable. So 1, if X is a closed subshift with the right almost star specification property, and at least two invariant measures.
Ergodic or not necessary?
Ergodicity is not necessary. Yeah, so that's actually a good point. Is for example, here we don't even necessarily have that the generic points are full measure, right? Because certainly if it's not ergodic, this isn't true. But it turns out that if you have the right almost star specification property, there do exist generic points. This follows from this specification property. So we have at least two invariant measures, that is if we're not uniquely ergodic, right? Then for any invariant measure mu on X, we have that the generic points of the measure mu is pi 0, 3 complete. And I'm going to define this, that the irregular set I of xt is sigma 0, 3 complete. So we can sort of define other things than just the generic points. So in general, if we have V, a subset of measures on X, you know, if we look at the sequence of empirical measures of a sequence X, you know, it may not necessarily converge, but it does have limit points by compact, or if X is compact, if the space is compact, it does have limit points, right? By compactness of the unipole in the weak star topology. So if we have V in X, we can define G super V as equal to the set of X, such that, and also let's define V of X equal to the limit points of the sequence Xn. Right, so we define G super V to be the set of points where V is contained in V of X. G sub V is the points where V of X is a subset of V. And we define I of xt. This is our set of irregular points. So this is going to be the union overall phi, overall continuous bounded functions on x of I phi of xt, where I phi of xt is the set of x, where the limit as n goes to infinity of the integral of phi d, these empirical measures, does not exist. Right. So this is the irregular set. It's the set of points where if you have some continuous function phi, you can sample along the orbit of x and you don't get a defined limit. Right. And so for example, for any ergodic measure, mu of this irregular set is going to be 0, for example. All right. So what we show is, going back here, that G of mu is pi 0, 3 complete, and I of xt is sigma 0, 3 complete. Now how does the actual proof go? It's not too tricky. So here's the idea. So let's take C. Also, can people see this chalk? Is it hard to read?
That was a little rough, yeah.
Okay. So let's C be our pi 0, 3 set that we talked about earlier, the set of sequences which are infinite in limit. Right, so this is a pi 0, 3 complete set. Right, so we showed earlier, right, so because T is continuous, it's a very simple computation. It's exactly like the case for normal numbers in base B to show that G of mu is pi 0, 3. So we already know it's pi 0, 3. We just need to show it's pi 0, 3 complete. So we're going to find some map pi from n to the n to x continuous such that if beta is in C, then pi of beta is in G of mu. And if beta is not in C, then pi of beta is in I of xt. This actually gives us both of these statements here. Once we know that I of xt is sigma 0, 3 complete, but again, that's a sort of a simple computation. Right, because we've shown that if B is in C, then pi of beta is in G of mu. If B is not in C, then I of xt is disjoint from G of mu, right? G of mu, every continuous function has a well-defined limit along an orbit of its generic point. So if we show this, then we're going to get the statement of the theorem. So here's the idea. But I do still have the statement of right almost star specification up. Okay. So we're going to define three sequences, AN, BN, and CN, all quickly increasing, and I'm going to give the exact conditions on them in a bit. But what we're going to do is we're going to let U1 be equal to X from 0 to AN. Oh, sorry. Before that. So, before we define these sequences, let mu be our measure of interest that we want to show the generic points are pi 0 3 complete. And pick nu not equal to mu. That's an invariant measure. And we can do this because there's at least two, right? Alright, so now because we have right almost star specification, we know that for both of these measures there exist generic points. This is a theorem. It's a slight generalization of Sigmund's theorem, which says that if you have the specification property, then this holds. Right. So pick x in G of mu and z in G of nu. Okay. So now we define our three sequences: AN, BN, and CN. And we let U1 equal X from 0 to A1, repeated B1 times, U2 equals Z from 0 to C1, U3 equal X from 0 to A2, B2 times U4 equal X, or Z from 0 to C2, and so on. And so what we're going to do is that, with judicious choices of A1, B1, and C, or AN, BN, and CN, we're going to use the specification property to paste these all together. And the idea is that if beta goes to infinity, then this 0 to C1 portion is going to be some non-trivial fraction of this portion over here. Right? So in this segment of the word, everything is going to be distributed according to mu, right? In this segment, everything is distributed according to nu. And so if this is a non-trivial fraction of the length of this guy, then we're going to get something other than mu when we sample along that subsequence, right? Is that? Let me actually give the conditions.
So when you're racing to parse this, you're defining a word that is the beginning of X, but repeated many times.
Yeah.
Then the beginning of Z, and then a longer stretch of X for many more times, and then longer.
Yeah.
Okay.
Yeah. And I'll try to make it clear, like why we do this. So here are the properties that A is going to need to satisfy. So we choose AN quickly growing, so that 1, AN plus 1, is greater than or equal to 2 to the n plus 1 times the sum of all the previous ANs. Okay.
This is the condition of the growth, right?
Yeah, it's saying that AN grows very quickly. So the idea is that, if we want to study what happens at the end of, this stretch here, we only need to care about this actual part. All this stuff gets washed out because it's very small compared to this. So 2, AN is at least 2 times this n of 1 over 2 to the n, where this n of 1 over 2 to the n is taken from the right almost star specification. So what it's saying is that, we can actually do things with the specification property using these x from 0 to ANs. 3, we have that if we look at the empirical measure of x, m, for an orbit length m, this is 1 over 2 to the n close to mu in the Prohorov metric. I didn't define this, but it's just sort of a nice metric you can put on measures on your polar space, which turns the set of measures into a into a polar space
So
itself.
it's a metric for weak convergence, right?
Yeah. It generates the topology of weak convergence. And I can give the definition if you want. It's not hard to state. Right, so this is true. And the same is true if we replace x with z and mu with nu. Right? So we just want both of these conditions to hold. So if we look at a long stretch of x, this should be, the empirical measure of this guy should be close to mu. Okay. And now this is just defining our sequence an, and then we're going to want to define bn so that an times bn is at least the maximum of 2 to the n times an plus 1 and 2 to the n times the sum of all the previous ai bi's. And finally, I don't want to erase this stuff yet. Finally, we're going to let Cn be equal to the floor of an times Bn over beta of A. Okay. Now what we do is we apply specification. So we start with some word W in G, which we know is not empty. In order to have the specification property, we need G not empty. So we start with some W in G, and then we append to it x0, a1. But we change this a bit. So v1 is epsilon close to x0 to a1 in Hamming metric, right? And then we want to do v2, where we do the next copy of x0 to a1. And again, because we can apply right on the start specification as long as these blocks are greater than some length, right? So we can always make them longer to still apply specification. That's why this thing is so nice. We just do the same thing, So we just keep going on and on and on, applying specification inductively for each copy of x0 to a1. And then for z0 to c1, and then for x0 to a2, and so on. Okay, is this making sense? Okay. Now, we also have that x is a closed subshift, and so in particular, this actually does define a point in x. Right, we can take a limit. We can take an intersection of the cylinder sets associated to the nth step in this construction, and it will have a non-empty intersection. Okay, so let's let pi of beta be equal to this sequence that we construct. So I claim that this is a good map. So it's continuous, right? Since if we just change, some finite number of beta of n's, this is only going to go so far out into the sequence, right? The only place that beta actually comes up is in Cn. And so you're most going to be changing a finite number of these CNs, and so it is continuous map. So it's continuous. So now what if beta is in C? That is, the limit as beta goes to infinity, or the limit as n goes to infinity of beta of n is infinity. Well, in this case, Cn is going to be some asymptotically, a trivial fraction of an times bn, right? And so in particular, no matter where you look at the sequence, say that this is your first A1, B1 segment, and then this is C1, and then this is your A2, B2 segment, and then C2. The point is that as n grows to infinity, this portion is going to take up a smaller and smaller fraction of this initial segment here, right? And so in particular, the part where you're approximating nu is going to 0, and approximating mu is tending to 1. And so this implies that pi of beta is going to be in g of mu. Does this make sense? Okay, on the other hand, if beta is not in C, then there's some value that beta then takes infinitely often. And so in particular, if you sample first along the ends of the A and Bn portions, you're going to be close to mu, and tending towards mu. But if you sample along the ends of these Cn portions, you're going to be tending to something that's not mu. It's going to be some non-trivial convex, not trivial element of the convex hull of mu and nu, right? And so in particular, what this means is that if you take some block and its indicator function, this doesn't have a well-defined average. Well-defined limit. So pi of beta is in pi x t. Okay. That's the end of the proof. So that's it. Now very quickly, I just want to state the other theorems that we proved. I won't give their proofs, just in the interest of time. So we also have part 2 of this theorem. If x is a g delta subshift, so it's not closed anymore, it's just g delta, with periodic specification, which is a stronger condition than right almost star specification. And at least 2 invariant measures. Then for all mu in T of x, we have that g of mu is pi 0 3 complete. The proof of this statement is just very, very similar to the proof I just gave. You just have to kind of fix things to work with the g delta versus being a closed subshift. And the last theorem I'm going to state is that if a Polish dynamical system xt has the strong approximate product structure, which I didn't define, and I won't define because it just will take up another board. But it's another type of specification property that is similar to one that people have studied before. Strong approximate product structure. Then for every closed connected subset V of our invariant measures with non-empty complement, is pi 0, 3 hard, right? Where G sub V was the set of points where your invariant measures are contained in V. Furthermore, if you assume that X is compact, this is actually pi 0, 3 complete. If X is non-compact, we have an example where this doesn't hold. The problem is that this set also includes the measures where there is no limiting measure, which can happen in a non-compact setting. The set of limit points could be empty, and this makes it pi 1, 1. So that's the last theorem I'm going to state. Just as an application of these theorems, we do get that the set of points which are normal for the continued fraction expansion is pi 0, 3 complete, and for the beta expansion is also pi 0, 3 complete. Okay, and that's it.